I'm Rohit Kumar Singh, the teaching assistant for the course Statistical Mechanics. And this course is taught by Professor Dipanjan Chakrabarti uh, at over the NPTEL platform. And this is the third live session where we interact uh, with you guys and we recap some of the concepts of what is being taught at NPTEL and then show some example problems. So, so let's start for today. So today I'll try to recap the Maxwell relations and what Maxwell's relations really mean and how can we use the Maxwell relation in the problem solving. So I'll solve some problems based on them. Okay, so yeah, let's start. So first, before going to Maxwell relation, I'll discuss a very important concept, which is called the legendary transform. So so this is also discussed in the lectures, but just to remind you. So what Legendre transformation means is that given a function fx, okay, we can always find another function g of m which will be equal to f minus x del of del x. So what we so in Legendre transformation, what we do is we replace our original function with a new function by changing the variable, by changing the dependent variable. So here the dependent variable was x, and now our dependent variable is m, where m is del f by del x. Okay, and this g is an equivalent representation of this f. So for an example, so this example was also given in the course. So that the example is that suppose you have a equation of a curve like this. So y is equal to x square. Okay, so this equation is your, suppose this y is your fx, right? Now there's an equivalent way of constructing this curve using the tangent at all the places on this curve. So if you can find tangent at all the places in this curve, then you can basically retrace the curve. And so we find another function using the same using uh, this recipe, f minus x del f by del x. Okay, and so here our f is basically ax square, right? And so this g is basically uh, f minus x of, and then if you differentiate, del f by del x is just 2xa or 2ax. Okay, and then by doing some arithmetical manipulation, you will find that this is this is just simply y is equal to minus 2ax square. Okay, and then you need to replace the x by m using some mathematical manipulation because we know that m is equal to del f by del x. So m is equal to 2xa, and so for x you can write m by 2a, and you can put here and you will get the gm. Yeah, anyone has any question? Someone raised his hand. So if you have any question, you can directly unmute and ask. Okay. And okay, what I'm basically want to say is, so doing the legendary transformation, we find an equivalent way of representing any function. Okay, such as we find a way to represent this curve using the function depending on the slope at all the points. Okay. So similarly, you might have studied, if you have studied classical mechanics, there you have Lagrangian, which is a function of q and q dot, right? The generalized coordinates and its time derivative. And then we do a Legendre transformation to obtain something called Hamiltonian, which is a function of q and p, which is a generalized momentum. So we basically replace q dot, and the recipe that we use is the same here, this one. Okay, by doing this basically. Okay, and this is what we have what we call is the generalized momentum. Okay, so this is what Legendre transformation in classical mechanics gives us. Okay, the Hamiltonian, and we know that there is an advantage that because the Hamiltonian follows first order equation. I mean the Hamiltonian for the equation of motion in terms of Hamiltonian are first order differential equation, while the equation of motion in terms of Lagrangian are second order differential equation, if you remember the Euler-Legendre equations, right? So yeah, this is very helpful. Now in thermodynamics, similarly we can have different kind of potential. So potential are basically thermodynamic functions, right? So first, for example, if you have internal energy SVN, so now internal energy is a function of entropy, volume, and particle number. And if you want, you can replace V. So so we can replace V in this internal energy with some other quantity. So for example, and to do that, we'll follow this procedure of Legendre transformation, and we see that if you simply write this, so keeping others constant, and from first law of thermodynamics, you know this is just minus P, right? This is minus P. So you have U plus PV, and this is another quantity which we called enthalpy. Okay. Sorry. So so these things are done in very detail in the lecture, so I'm just writing it out for refreshing the memory. So if you guys think that you understand all of this and you don't need me to recap this, you can tell me and I will straight go to the problems. Okay. Is that fine? And if you have any question, you can also ask. Okay. Okay, so so similarly, then again, if you have if you want to replace some other variable here, suppose if you want to replace the entropy, similarly you can do that. You can have this Legendre transformation in terms of entropy, keeping others constant, and this again you know from first law of thermodynamics. It's just the temperature, so U minus Ts, and this is what we call the Helmholtz free energy. Okay, what else? So now if you want to replace both of them together, you can also do that. So entropy and volume together, and the recipe remains the same. So U minus S del U del S minus V del U del V, and you get this, which is called the Gibbs free energy. So these are different, potentials in thermodynamics, and they have their own usage, as you will see later. Okay. Uh, for example, let's take the Helmholtz free energy. If you have a finite change in the Helmholtz free energy, that will lead to finite change in internal energy minus TdS minus SdT. Okay, and from first law of thermodynamics, you have TdS. Sorry. PdV right? This you have from first law of thermodynamics. And so if you substitute here, what you get is so TdS will cancel with TdS, and you will get what remains is minus SdT. So we substituted du from here, okay? Minus PdV plus mu dn. Okay? So now what you find from here is that a finite change in Helmholtz free energy, it depends on change in temperature, volume and number, okay? So this Helmholtz free energy is always conserved. So it is conserved if there is no change in temperature, so isothermal process, and there is no change in volume. So that means no work is being done, so no mechanical work. Okay, and similarly you can find the expressions for others. So I'll just write them. These are done in the lectures, but I'll just write them out for you. So similarly, Gibbs energy is given by this formula, right? And Gibbs energy is a function of TPN. So remember, we changed the in the internal energy we change S and V, and in place of S and V we got T and P, temperature and pressure, right? And so this is conserved. In an isothermal process, because it's a function of temperature. So if there is no rise in temperature, it is basically conserved. And also if there is no change in pressure, that means there is a constant force applied on the system. Similarly, the enthalpy, which is given by this, and it is now function of SPN. So for enthalpy, we changed the internal energy. I mean, in place of volume in internal energy, we change it to pressure using the Legendre transformation, and so we got this new potential here, which is enthalpy. And as you can see here, it should be conserved when there is no change in entropy, or there is no change in change exchange of heat in the system. So it will be conserved in adiabatic process, and in the presence of constant force, like, because we need to keep the pressure constant. So yeah, so this is the physical meaning of all these free energies, okay. And yeah, that is all for now. Also, there is a something called grand potential, which is a function of temperature, volume, and chemical potential, and this is given by just minus PV, okay. And as you can see, since it depends on temperature, volume, and chemical potential, so this is conserved. Someone raised a hand. Do you want to ask something? Please unmute and ask if you want, if you have any question. So yeah. So since this is a function of temperature, volume, and chemical potential, so this should be conserved in isothermal processes, where there is no rise in temperature and no work is being done. So volume remains constant, no mechanical work. Plus, chemical potential will remain constant if there is no chemical exchange. So there is no, production of new particles or exchange of new particles. So no chemical work. Hi, do you have to ask something? Someone is raising his hand. I don't know the name. Okay. So yeah, okay. So this is these are our four new potentials that we got from the internal energy using the Legendre transformation. Okay, and these are used extensively in thermodynamics. They have their own importance. Now, what are the Maxwell relation, and how do we derive the Maxwell relation, and how Maxwell relation actually emerge from first law of thermodynamics, basically. So okay, so briefly I will discuss that. So basically, first law of thermodynamics is very powerful. Okay, so let us write it again. So we have change in internal energy is equal to TdS minus PdV plus mu dN. Okay. Sorry, yeah, I made a mistake and no one noticed. Here I wrote it wrongly. This should be like this. So you guys need to put little bit focus. You are not noticing anything. I wrote the first law of thermodynamics wrong here, but no one pointed it out. Okay, so this is the first law of thermodynamics, and in the last week I discussed that this uh, internal energy is a state function, right? It only depends on the state of the thermodynamic system, not on the path taken. Okay, this is a state function, and so uh, we can we can have the finite change in this state function, and we know that it depends on SVN. Okay, it's a function of entropy, volume, and particle number. And so finite change in internal energy we can write like this. Right here, B and N constant. Here S and N constant, and then with respect to number, here S and V constant. Okay, now since this is a state function, sorry, it should, I mean, it needs to be an exact differential. So we discussed this also last time, that sorry, that those functions which are exact differentials, they don't depend on the path. Okay, so this change in internal energy does not depend on the path taken by the system. So that's why it is an exact differential. And so there are some criterias for exact differential to hold. So for example, if you have a exact differential df uh, given by so you have f of xy, right, and finite change in f is given by this. Here a and b are some arbitrary function, and if this is an exact function, exact differential, then this criteria will always satisfy. Okay, now since here we have three terms, so here this criteria will satisfy for all the three. I mean, in if so we can write, three equations like this. Okay, so let's try to write them. So first, let's take these two. Okay, so here our A is del u by del s, and our B is del u by del v. Okay, and this, if we write here, we get del by del v del s, and here v and n is constant, and here s and n is constant. Remember, in partial derivative always something should remain constant, right? Okay, and then using the first law of thermodynamics, du by del s is just the temperature, right? So you get this, and du by del v is just my negative of pressure, so we get this. Okay, so this is our first Maxwell relation basically, and similarly you can use these two and then these two, to have the other two Maxwell relations. So I'll just write out them because it has been done in the lectures. So I'll just write what the other two relations are here from here. This is the second Maxwell relation, and then we have this is the third Maxwell relation. Okay. Now, so so these three we got only from the internal energy. Okay, but we have these other four free energies also available, and these four will also give us three equations like this, right? So in total we will have 5 into 3, 15 equations. But all of them will not be, independent, or all of them will not be different from each other. Okay, and so to check how many of them are independent, so in the lectures, if you go and see the lectures, I mean, it's a long derivation, so there is something called Jacobian formulation that has been used. So basically, in Jacobian, what happens is, I mean, the relation from the Jacobian, what has been used is, so suppose you have this Jacobian here. So everyone know what Jacobian is like. So for example, Jacobians are used in coordinate transformation. So this is just the determinant of del A by del X and del F by del Y, del G by del X, del G by del Y. Okay. And so using this, one can show that all of the 15 relation are not independent. So I'm not going to do that. You can refer to the lectures. What I will do is I will just write the other independent Maxwell relations for you, okay, so that we can use them while solving the problems. So yeah, okay, so the fourth Maxwell relation, which we get from the Helmholtz free energy, uh, is this. Sorry. Okay, this is the fourth, and then the other two are other two we get the one of them we get from Gibbs free energy relations. This is this one. And one we get from the grand chemical potential, the grand potential, which is this. Okay. So you notice that from enthalpy we don't get anything. Okay, so from the enthalpy, all the relation that we get, they are dependent on others. So enthalpy doesn't give us anything. And these are the Maxwell relations, six Maxwell relations that we have. Okay, and we will use it in solving some problems. Okay, so anyone has any question up to here? Any doubt? Please ask if you have any doubt. So, I mean, you can ask why we have this Maxwell relation. What is the importance of having this Maxwell relation? So that will become clear in the problems that we are going to solve. But you can see here, like, so so from the first Maxwell relation, you see uh, there is an equality between change in temperature with respect to volume and change in pressure with respect to entropy. Now, uh, you cannot measure directly this thing, right? The right hand side. I mean, how do you change entropy? I mean, it's not from in a lab. It's very tough to quantitatively change entropy. But what you can do is you can change volume, right, of a system. So you can use a compressor to compress a gas, and then you can measure temperature. So you can calculate this thing, which will be equal to this thing. So by measuring the change, I mean rate of change of temperature with respect to volume, you can basically measure the rate of change of pressure with respect to entropy, change in entropy. So so that's how, I mean, these uh, all these Maxwell relations are very important. Okay, so they all of them, you can see, you can take anyone. So here also you see that there is a change in chemical potential with respect to entropy. This you cannot measure, but this you can measure, right? You can change the number of particles, and somehow you can calculate, because you can do calculations using molar equations, and you can notice the change in temperature, and then you will calculate the right hand side. So that's how these Maxwell relations are very important, and we will use them, okay, in problems. uh, okay, so no one has any other question, right? No one is asking any question. I think everyone understood it. Okay, that's great. So let's go to the to our problems. So here here we have first problem. So you need to show this relation, okay, using Maxwell relations, and CV is the specific heat at constant volume, and we have to find the derivative of this CV with respect to volume, okay, at fixed temperature, and this should be equal to this temperature times second order derivative of pressure with respect to temperature. So it looks very complicated. So how do we attempt to solve it? Any idea, anyone? I mean, first obviously we will write this left hand side. We can write, so in place of CV we will put del U by del T, right? Constant volume. And then what should we do? So you have these Maxwell relations. Do you think you can use any one of them? So, uh, but first, also, what from the, you know, from simple first law of thermodynamics, you also have this. So, suppose I mean this is so suppose we assume that dn is 0, so we are not varying the particle number, okay, in this problem anyway. uh, so this is the first law of thermodynamics, and you can write this from here. Okay, so you have something here, you see, that resembles this right hand side. I mean, it's not completely that thing, but it's temperature times something. So we know that we can use this uh, thing here, but from the LHS we have this thing. We don't have del u by del v, we have del u by del t. But you notice that there is a second order derivative of del v. So and there is a famous theorem. uh, I mean, we can basically exchange the derivative here, so we can write this. Do you know the name of this theorem? Anyone? It's called Clairaut's theorem, and it holds if your function is very smooth. So u is a smooth function, so that the partial derivative should be continuous. But that we don't have to worry, because I mean, we know that internal energy is always a homogeneous function, so this will always hold. Okay, and now you have this in LHS, and we have this from first law of thermodynamics, so we will put uh, this here. Okay, so now LHS we get del by del t times del v minus v. So we just substituted this here, okay, in place of here. Everyone is fine till here? Let me know if you don't understand anything. Now, okay, now we have something where we can use the Maxwell relation. Okay, so let's go to our Maxwell relations. So we have del S by del V. Now in the Maxwell relation, we see that the sixth Maxwell relation, del S by del V is del P by del T, right? And this is exactly what we want. So we will replace this by, because in the problem you see we have del P by del T. So we replace this by del P by del T minus P. So we have used this Maxwell relation. Okay, this is the sixth Maxwell relation. And now you see that this is straightforward. You can see that this is the RHS. So if you differentiate it, So first you have this, then you have and then you have del p by del t. So this cancels this, and what you left is with is square, which is the RHS, right? See how Maxwell relation helped us here. And no, what this relation tells us is that if you want to know that how the specific heat of your system varies as you change the volume, you just have to measure this quantity which is measurable, right? It's just the second order derivative of pressure with respect to temperature. This you can, you know, this is easy to measure in lab, and this temperature you can measure also. So yeah, this is how Maxwell relation helps you. So this, it has very wide application everywhere. So everyone understood this problem, or anyone has any doubt? Hello guys, are you able to follow? Okay, yeah, thank you. So if you have any question, or if you don't understand anything, please ask, okay? Okay, so if this is fine, then let's move to the next problem. Uh, okay. So here the problem is, using the Maxwell relations, derive an expression for the change in entropy S of an ideal gas as a function of volume and temperature T. Now, for an ideal gas, the internal energy is a function of temperature only, okay? And we have to show this thing, okay? Uh, sorry. Oh, sorry. This is the sixth Maxwell relation, right? That I just discussed. So yeah, this is we already have discussed. So using this, we have to find the expression for the change in entropy, okay, delta S. Uh, and what is given is it is an ideal gas, so internal energy is a function of temperature only. And okay, and for an ideal gas, we have this equation of state, right? PV is equal to nRT. From here, we can calculate del P by del T, which is nRYV. Sorry. Yeah. Okay. And if you put this in the Maxwell relation, then you have from here nRYV, right? And since there is no temperature here, so this becomes an from the partial, this no longer remains a partial derivative, right? There is no because temperature is not there in the equation. So this is ds by dv simply. And so we have ds is equal to nr dv by v, right? So this is the finite change in entropy. And so if you notice here, for an ideal gas, the change in entropy only depends on the change in, relative change in volume, dv by d. Okay. So for a finite change, for a large change, you can just integrate it from v1 to v2. nr is a constant, and this will give you log of v2 minus v. Okay. So so you see, this is only entropy is always positive, as you can see here. The v2, this is positive only when v2 is greater than v1, right? And the logarithm of negative doesn't make any sense. So this should be always positive, and so this is v2 is always greater than v1. So it is the gas will always expand, and which will lead to a change in entropy, and the entropy will increase. So yeah. Someone has written, sorry, what you want to ask? It means S is directly proportional to R, L and V. No, this is not true. Change in always the change. We cannot you cannot write entropy you cannot have a expression for entropy like this. You can always measure the change in entropy. Okay, so only the change in entropy that we can write it here like this. It doesn't mean that S is R, L and V. It is not true. Because you see, so that's why there is a log function here, right? It is not linear. So if you think this is true, then we can write S1 is equal to nr ln v1, S2 is equal to nr ln v2, and then S2 minus S1, which is your delta S, will be nr ln v2 minus ln v1, which is not the same thing, right? This is not the same thing that we got here, which is ln v2 minus v1. Okay, so no, this is not true. Okay. Yeah, this is nice. So yeah, guys, if you have any confusion, please ask. Don't hold back. Okay, so if you have no other question here, so let's move to the next problem. So yeah, sorry. So here you have a S over E. So E is the internal energy basically. This is E is same as U. Okay. And internal energy, sorry, entropy is plotted as a function of internal energy here. And we need to uh, tell how the temperature for the three phases are related to one another. So which has higher temperature, which of the following phases have higher temperature? Okay, so anyone has any idea about this? Okay, someone wrote we can use the del S is equal to, no, but we don't know del Q. But it's okay. From first law we have simply this, right? This we have, right, from first law. Yeah, same thing. Okay, keeping the volume and number of particles constant. Okay, so now think about it. So this is del U over del S, or del S over del U is just the slope of, it's just the slope of these functions, right? And for B, since B is flat, del S over del U is basically infinite, right? Sorry, no, it's 0. Del S over del U is 0. So 1 by T is 0, and so T should be infinite. Yeah. B is constant, so yeah, obviously. So we know that either this or this would be true. And now we see that for C, the internal energy is greater than A, right? Basically, for phase C, UC is greater than UA. So more internal energy means more temperature, right? So that means C is the correct answer. Is that fine? Okay, so uh, this is a easy one. Let's go to the next problem then. Now here the question is, for a particular thermodynamic system, the entropy is related to internal energy and volume by this expression. Sorry. Okay, so internal energy is given, entropy is given by this relation, depends only on the internal energy and volume. Okay, fine, where C is a constant, and we need to find the Gibbs potential. Okay, so we have to find what? We have to find temperature, because expression for temperature is not given. Entropy is given, we have to find the expression for pressure. Okay, and yeah, so let's see how to solve this. So any idea, anyone? How do we find the Gibbs potential for this system? How do we proceed, anyone? Yeah, so Aditya wrote using the using the first law of thermodynamics simply. Yeah, this is fine. Yeah. So what do we have from here? So we have du over ds is equal to temperature and constant volume. But since we have s as a function of u, so we can invert it and we can write it like this. So 1 over t, sorry, 1 over t is equal to del s over del u, and then we just differentiate it. So what you get is c into 3 by 4 u. 3 by 4 minus 1 is minus 1 by 4, and v 1 by 4. Okay, so basically temperature, what you get is 4 by 3c, and u by v whole to the power 1 by 4. Is it fine? Mm, yeah. Okay. And then you have also from here del u by del v is equal to negative of pressure. So okay. So let's write it in terms of you know entropy basically. So so we have u is equal to uh, is s by c v1 by 4 whole to the power 4 by 3, right? So this we have. Now we can calculate del u by del v. Also you can simplify it. C 4 by 3 and 1 by 4 into 4 by 3. So it's just 1 by 3, right? Is it fine? So what you have here is uh, 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 yeah. Okay, let's do it. So s by c to the power 4 by 3, and we differentiate the with respect to volume, so minus 1 by 3 v minus 1 by 3 minus 1, right? This is equal to minus p. So minus minus get cancelled, and we have p is equal to s by c 1 by 3, and to the power volume is simply minus 4 by 3, which becomes so so this is just s by cv 4 by 3, 1 by 3. Is it fine? Mhm. So yeah, so what I did is I wrote this expression of entropy in terms of internal energy. Okay, I inverted this equation to calculate this derivative del u by del u over del v, right? And so what I got is this. So pressure is equal to 1 by 3 s by 1 by 3, and then in the power of 4 by 3 we have s over c v. So yeah, this is what I got. So if we try to put them all together, what will happen? Let's see. So Gibbs potential energy is U minus Ts plus PV. So this is just calculation now. So internal energy we calculated here in terms of entropy. So let's write this. Yeah, S by S over S over C 4 by 3, and minus T temperature we calculated here. So four by 3 C U by V 1 by 4 S. So we can replace this U by in terms of entropy, so that we don't have U in anywhere in the equation. So we'll do that in the next step. And then we have pressure we calculated here. V. Okay, so this is what we have. So let's try to simplify it. So U again I'm going to replace by this expression. Okay, so it will be a big expression. Whole to the power 1 by 4. Okay, S is here. Okay, let's simplify the second term. So 4 by 3c. In the numerator, I will have s by c to the power 1 by 3, and then 1 over this will become 1 by 12, but then there is a denominator v 1 by 4, right? So uh, so that will add up with it, right? Wait, I think I did some mistake somewhere. Mm, this is fine. Yeah, I think it will add up here. Okay, and then s is here. Oh, this has become too complicated now. Okay, let's see. P we have calculated correctly. I think. Yeah. Okay, let's see what we get. For s by 3c. Here we have s over c 1 by 3. Yeah, I think we will get this. So now this is sorry. This is 12 1 3. So this is basically 1 over 3, right? Yeah. Mm-hmm. Picture is getting clearer. Okay. Now you see. Yeah. So, okay, let me write once more. This is 4 by 3. This s and this s combined, and this c and this c combined, we can write it as 4 by 3, and then you have 1 by 3 plus 1 by 3 s by cv 4 by 3. Okay, and this v and this v, if you combine, s by c 4 by 3, this is just 1 over 3, right? So, and this is same, so 1 minus 4 by 3 is 1 by 3 s by c 4 by 3 1 by sorry minus 1 by 3, and then you have plus 1 by 3 of the same thing. So this cancel this and you get 0. Whew. Did everyone follow? Yeah. So yeah, I thought I did some mistake because but yeah, it all fell through nicely. Okay, so yeah, so the Gibbs potential becomes 0 for this. Well, this is nice. I mean, hmm. But why we get zero Gibbs potential for this kind of entropy? Anyone has any clue? So what did I tell you about the Gibbs potential? Do you remember? I mean, so this is also a state function, okay? These all the other thermodynamic potentials. These are all state function like potential energy and entropy. So so for this kind of entropy, which depends on u and v, we get zero Gibbs potential, okay? But as the system will evolve, this will also change. This Gibbs potential will change. It happens to be zero at this at some point, but if the entropy will change, then this will also change. But the thing is, it will be always zero when if you have a isothermal process and there is a constant force. So the pressure, if you keep pressure constant, so if you evolve your system keeping the temperature constant, so you keep it isothermal and the pressure is constant, that is there is a constant force applied on the system, then you the Gibbs potential will always be zero, okay, for all the future time, however you take the system. Okay, so yeah, this is a nice exercise. It was little long. So do you have any question, you guys? I'm done from my side. If you have any question or doubt, we can discuss and talk. Anyone? So okay. So if you don't have any question or anything to discuss, we can close the session today and let's meet next Saturday, same time. Okay. So bye bye everyone. Uh, Thank you for joining. See you. Thank you. Bye.